In this chapter, we will see how to price bond options in binomial trees. Highlights, so we're gonna see once again what the options basics are. Then we're gonna see how to replicate the payoffs of a European bond option. Next, we're gonna see how to price an American option and the difference between European and American. And finally, we're gonna see how to hedge with options. So this is gonna be how to compute delta, Vasicek, and gamma Vasicek. Here we review some of the option basics. So once again, the exercise price is K, the strike price. B is gonna be the bond price. Here we have the payoff of a call option, which payoff is defined as the maximum between the bond price and the strike, and a put option where the payoff is computed as the maximum between the strike and the bond price. Some option basics. We have to distinguish between European and American. So European are only exercisable at maturity, whereas American are exercisable anytime before maturity. There's also Bermudan options, and these ones can be exercised at some fixed points in the future. So for example, at coupon payment dates. And finally, there is put call parity for European options, and this is also going to apply for bonds, where we have that the call price is a function of the put price plus the bond price, and here we have the discounted strike price. There's some other trading strategies with options. This one is called straddle, and straddle is a very interesting one because you buy one call and one put. You end up with this payoff. Actually, the call and the put have to be at the money, and this trading strategy is basically betting on volatility. So basically, if the volatility you expect to happen is greater than the one on the market, you're going to end up making money. But volatility has to be high because remember, here you have to pay a premium to get by this call and this put. Options are usually traded on futures, so they're called future options. So these are the ones that traded on the exchanges. The payoffs are then defined with the future price of the bond or the underlying, both for calls and puts. Normally, options on actual bonds are usually OTC, that means over the counter, so there's not an exchange market for them. How do you price European options? So the logic is going to be exactly the same than the one for equity options. So first you have to figure out the value at expiration. So you construct your tree and then you figure out the value. Let's say this is expiration. You figure out the value of the option here, and then you need to start moving backwards in your tree until t equals 0 to get the price of your option. Now, here we're going to be using the replicating portfolio to be able to move back in the tree to get our option prices. Note that this value of the option is not going to depend on probabilities. Everything is going to be done with the replicating portfolio methodology. To price American options, it's going to be very similar to European options, but you need to do an extra step. And the extra step is at each node, you're going to have the bond price, and you're also going to have the option price. A third thing you need to have is going to be the payoff if the option is exercised immediately. So for a call option, for example, it's going to be the maximum between B minus K, 0. And then you need to compare the option price with this price, which is the price of exercising the option immediately. And whichever is higher is the one that is going to prevail. So if this one is higher, this is the one that you will take. And you have to do this at every single node to make sure if it's better to keep the option or to exercise it. Hedging with options. So these are the formulas on how to compute delta Vasicek and gamma Vasicek. The logic is going to be exactly the same one that we used for bonds, but instead we're going to replace here with the price of the option. So for the case of calls, this would be the call price in the up and down scenario. And then the delta plus and delta minus have to be also computed like with C++ minus C minus plus and so on. Options can be very complex. So an advantage of hedging assets and liabilities that are also very complex is that it's going to reduce the number of transactions that you need to keep the hedge alive. Sometimes it's even better to hedge with options than to do your immunization with bonds. So in conclusion, we're going to see like how to price a bond option. We're going to see the difference between American versus European, and finally we're going to see how to do risk management with bond options. Next, we're going to run into a set of examples to further understand this material. So now we're going to run into some examples to further understand bond options. So imagine that you have an underlying that is a 2-year 0 coupon bond. It has a price at t equals 0 of 0.9058, and at t equal 1 it can take two prices, 0.9324 or 0.9835. Now you have a call option with strike K equal to 0.94, and it's gonna expire in 1 year, so the maturity is 1 year. And this option is going to be on the 2-year zero coupon bond. Finally, investors can buy or sell 1-year zero coupon bonds for 0.9576. And then they ask us, okay, what is the price of this call option? So to solve this, we're gonna study the cash flows of the 1-year zero coupon bond, the 2-year zero coupon, and finally the option. So the 1-year zero coupon bond, we know that at t equals 1, it's gonna pay $1 in the up scenario and $1 in the down scenario. That's given. The price at time 0, that means the 0D1, it's equal to 0.9576. Now for the 2-year zero coupon bond, we know that in the up scenario, it's gonna pay 0.9324, and in the down scenario, it's gonna pay 0.9835. And we also know that the price at time t equals 0, that would be the 0D2, it's equal to 0.9058. Finally, the option, so it's a call option. We don't know the price today of this call, so this is the only known. We only know that the price at t equals 1, it's gonna be equal to the maximum between the 2-year bond price minus k, 0. So this would be 0.9324 minus 0.94, which is a strike or 0. So this is gonna be 0 in the upper scenario. And in the down scenario, it's gonna be the positive side of 0.9835 minus 0.94. And then you take the positive side of this, and this is gonna be equal to 0.0435. Now, the next thing we're gonna do is the portfolio replication. So first, we're gonna do it for T1 up. So for T1 up, we need 1-year bond, and these are going to be the number of units, plus 0.9324 of the N2, that's the 2-year bond, and this has to be equal to 0. That's a payoff at t equals 1 in the up scenario of the option. And then at t equal 1 down, the equation is going to be 1 and 1 plus 0.9835 and 2 equal 0.0435. And 1 gonna be equal to minus 0.7937, and N2 is gonna be equal to 0.8513. Finally, to get our call option price, so C, it's gonna be equal to 0D1 and 1 plus 0D2 and 2. This is gonna be equal to 0.9576 and 1 plus 0.9058 and 2 that we just computed. And then we're gonna get that C is equal to 0.011. An interesting fact to notice here is that we're getting the call price by adding a 1-year zero coupon with a 2-year zero coupon. So this is like one of the magic things that we're doing here, that with 2 zero coupon bonds, we're able to replicate the price of a call option. For the next example, I'm gonna provide you with this tree. So this tree has all the information you need. For easiness, I don't give the discount factor names, but you should know that the first one is gonna correspond. So actually this is gonna be time. So this is t equals 0, t equals 1, and t equals 2. And then the first discount factor is gonna be like the 0D1, and the second one 0D2, and the third one 0D3, and so on. We're gonna price a call option, so in a second we're gonna see what that is. And then this one is gonna be the price of this, the 0D1, so this one is gonna be equal to the 1D1 in the up scenario. This one would be the 1D2, and this one the 1D3, and here it would be the 2D2 and the 2D3, and same thing for the other nodes. Now, what is the exercise about? I have a 2-year call on a 3-year zero coupon bond, and the strike is 0.94. So what does this mean? The 2-year call, it means that the maturity of the call is going to be in 2 years, and that the underlying is the 3-year bond. So that means that the option is going to expire at t equals 2. So then at t equals 2, I need to determine what is the price of that call option. So here, which one of these two is the price of a 3-year bond? So it's going to be the one that expires in year 3. In year 2, it only has 1 year remaining in the life of this bond. So then here I'm going to determine the payoff of my call option as max of B minus K, comma 0. And I'm going to do exactly the same thing, this node and for this node. So B, in this case, is going to be 0.8839 minus 0.94. It's going to be 0. So for the first node, it's going to be 0. For the second node, 0.8324 is also going to be 0. And then for the third node, it's going to be 0.9835 minus 0.94. The positive side of this is equal to 0.0435. And now I want to determine the prices of the call here in the up and down, and then at time t equals 0. So how do I go about doing that? So first, I need to set the equations of the replicating portfolio for C11. So I'm going to use the discount factors that I have in here. So I'm going to use this price and I'm going to replicate it with this bond, the 2D2 and the 2D3 in the up and down scenarios. So the equations would be 0, since that's what the option pays, equals, and then the other one is also going to be equal to 0. So I'm going to put the equation so that you know what they are, even though I know that the weights are going to be 0. So it's going to be 1 and 1 plus 0.8839 and 2, and then the one in the down scenario is also going to be 1 and 1 plus 0.9324 and 2. So n1 equals n2 equals 0. So in this case, C11 is equal to 0, right? I mean, we didn't have to do all this, but I'm doing it for completeness. Now, as for C12, the two equations, two unknowns in the up scenario is going to be 0 equals 1 and 1 plus 0.9324 and 2, and 0.0435 equals n1 plus 0.9835 and 2. And then from here, I obtain that n1 equals minus 0.7937 and n2 equals 0.85127. So C12 is going to be equal to 0.9576 n1 plus 0.9058 n2. This is equal to 0.01101. Now, the only one remaining is the computation of the call price at time t equals 0. So I need these two option prices I derived for C11 and C12 in order to be able to get the price at time 0. So the cash flows are 0 and 0.01101, and this is equal to n1 up and down, and then n2 I need 0.9078 up scenario and 0.9576 in the down scenario for bond 2. And then from here I obtain that n1 is equal to minus 0.19295 and n2 is equal to 0.21255. So that means that the call option has a price of 0.9324 and 1 plus 0.8639 and 2. Hence the call option has a price of 0.003713. Now from the same tree, I want to do another exercise where I have a 1-year call on a 3-year bond, and the strike is 0.85. So here the question is, the first question you must ask yourself is, when does the option expire? Because that's where you're going to have to start in your tree. So the option expires at t equals 1. And then the second thing is, what's the underlying security that you're going to have to use to compare the strike with? So the underlying security is still going to be the 3-year bond, but now not at t equals 2, but at t equals 1. So if we go back to the tree, now I need to work my call option starting here, and I need to compare it with the 3-year bond. So the 3-year bond is going to be this one and this one. So let's go and set up our two equations, two unknowns, to figure out exactly what's going on. So I have to compare against these two prices of the 3-year bond at t equals 1, 0.8238 and 0.9058. So let me put it down here. So at t equals 1, the 3-year bond, the 1D3, is equal to 0.8238 in the up scenario, and in the down scenario it is equal to 0.9058. Now we know that the strike is 0.85, hence the payoff of this call is the maximum between 0.8238 minus 0.85, 0, so it's going to be 0. And in the down scenario is 0.9058 minus 0.85. The positive side of this is gonna be equal to 0.055. And now the question is, what's the price of this call option at time t equals 0? So now I'm gonna use the replicating strategy. So for the op scenario, I'm gonna use the 1, and in this case the 3-year bond, just to have a change of plans. This is the cash flow of the call in the op scenario, and I'm gonna replicate it with 1 and a 1. And now I'm gonna replicate it with the 3-year bond. So the 3-year bond, according to the scenario, it pays 0.8238 and 3. And now in the down scenario is 0.0558 equals to 1 and 1 plus, and in the down scenario the 3-year bond pays 0.9058 and 3. So then from here I get that N1 and N3 are equal to minus 0.56059, and N3 is equal to 0.680488. So finally my call option is going to be equal to 0.9324. This is the 0D1 N1 plus 0.7968. This is my N3, and this is the 0D3, and this is equal to 0.019522. Now we're going to use the concept of put call parity to further price our bonds. So let's first state what the put call parity is. So the put call parity says that put option is going to be equal to minus the price of a bond plus the price of a call plus the PV of the strike. So then we're going to see how to understand this in the context of our trees. And specifically, I want to know what the price of a put option with strike equal to 0.94 and time to maturity equals 2 is. Notice that before, in the first example, we already computed the price of a call option with strike, same strike, 0.94, and same maturity. So this is one of the conditions that needs to apply for using put call parity. So here I want to determine the price of the put. Here I'm going to put the price of the bond. What bond is this going to be? It has to be the underlying bond, and I didn't specify here, but the put option I want to compute is the underlying is the 3-year bond. Here I'm going to put the call price of the option that has a strike of 0.94 and a time to maturity equals 2 years, and the underlying is the 3-year bond. And finally, I'm going to here put the PV of the strike. So let's start with the 3-year bond. So the 3-year bond is going to be all the discount factors that finish with 3 at the end. So it's going to be 0D3, 1D3, and 2D3. I go and get this from the tree. So this one is 0.8839, 0.9324, and 0.9835. This would be the 2D3. One step before, this one is going to be 0.8238 and 0.9058. This one is the 1D3. And then the one at time 0 is going to be 0.7968. Now the prices of the call options, those ones I also got from my valuation of the option before, and these are this node 0, 0, and 0.0435. This one is 0, this one is 0.011, and the price at time 0 was rounded 0.0038. Finally, the PV of the strike. So we know that at t equals 2, the strike, by definition, is 0.94. And then I'm going to bring it back in time. So at time t equal 1 in the upper node is going to be 0.8533. And down it's going to be 0.9001. And at time t equals 0, it's going to be 0.8121. Here the question is, how do you bring back this cash flow from t equals 2 to t equals 1? Like, what discount factor do you need to use? And here would be the discount factor, the 1D2, the one that brings cash flow from time 2 to time 1. So how would you bring the cash flow to time 0? It would be by using the 0D2, and you discount 0.94 to time 0 using the 0D2. So let's recall what the put call parity is. So the put call parity is where the put is equal to minus the bond plus the call price plus the PV of the strike. So down here, we're going to put those prices of the bond, the call, and the PV of the strike to figure out what the put option price is. So the 0.056, it's going to be minus the bond plus the call plus the PV of the strike. The 0.076, it's going to be minus 0.9324 plus 0 plus 0.94. And finally, this one is going to be equal to 0. We do the same for the other nodes. So this one is going to be 0.0 0.00295. The one down is going to be equal to 0.0054. And then the put price at time t equals 0 is going to be equal to 0.0191. So in this case, by put call priority, the put is going to be equal to minus the bond, so minus 0.7968, plus the call price, 0.0038, plus the PV of the strike, 0.8121, and this is equal to 0.0191. Now let's see an example on American options. So the difference between American options and European options is that early exercise can happen in these options. We're going to use the option that we just priced with put call parity, which is the 2-year put option on the 3-year zero coupon bond as underlying, where the strike is equal to 0.94. So one of the first things we're going to need here is the price of the underlying of the 3-year zero coupon bonds for each node. So the price is going to be all the TD3, so where T can take the values of 0, 1, and 2. So let's put those values. So these are the prices of the 3-year zero coupon bond. Why do I need them? Because now I need to evaluate first the price of the European put, which is the payoff, which is max of strike minus the bond price comma 0. But then because this option is American, on top of that, for each node, I need to evaluate, so the put American is going to be equal to the maximum between that put price that is coming from the tree. And then at each node, I also need to evaluate K minus B. Before, I only evaluated this max of K minus B at maturity, but now I need to evaluate it also for each one of the nodes. So before I only did it at T equals 2, now I need to do it at all nodes. So let's evaluate max K minus B comma 0, where K is 0.94. So I'm gonna get, for this scenario, 0.056, 0.0076, and for this scenario, 0. In principle, I should do synthetic replication in order to get the prices for the node before. Now, because I just computed the prices for this tree, in the exercise before, I already know that for the op scenario, I'm gonna get this price and this price when I do the synthetic replication of this put option prices. So I'm gonna get that if I do synthetic replication, I should get a price of 0.0295, and this is what I got when I did the put call parity relation, the 0.0295 from here. So this is for the op scenario. Now, what would happen if I exercise this option here? So if I exercise the option here, I'm gonna get the maximum between 0.94 minus 0.8238, which is the price of the 3-year bond in that scenario. So this is the 1D3, and this gives me 0.1162. So this is gonna be my price here. Now, in the down scenario, again, from before, I know that the price, if I do synthetic replication of these two prices, is going to be 0.0054. And then if I exercise my option at this node, it's going to be the maximum between strike 0.94 minus 0.9058. And then I'm going to get 0.0342, and this is gonna be my option price in this case because this one is larger, so I rather take this value, the big value, than the small one. So I would exercise my option according to the tree. So now the two new option prices changed from the European case. In the European case, it was this and this. Now, in the new one is P11 and P12. So now I need to get my put price at T equals 0. So I need to get two prices. So the first one is gonna come from replication. So let's do the portfolio replication here. So as usual, I'm gonna do the up scenario and the down scenario. So my values are 0.1162 equals 1 and 1 plus 0.8238, this is N3, and the down scenario is going to be 0.0342 equals N1 plus 0.9058 N3, and I obtained that N1 is equal to 0.94 and N3 is equal to minus 1. Hence, the price of this put would be equal to 0.9324 and 1 plus 0.7968 and 3. Hence, it's equal to 0.079656. So the first price coming from portfolio replication is the 0.079656. And now I could also exercise my option. So if I exercise the option, it's going to be the maximum between 0.94 minus the price of the 3-year bond at t equals 0.7968, 0, and this is equal to 0.1492. Since this one is larger than this price, so this is the second alternative, by the way, if I exercise, then the price of my put option is going to be this one. So in conclusion, price of the put, and this one is American, is 0.1492. And as you saw in the 3 cases, this one here, and this one here, we exercise the option. Why? Because we take the maximum between the put price that is coming from the replicated portfolio and the exercising of the option at that point in time, which comes from K minus B, the strike minus the bond price. Finally, we're going to compute the delta Vasicek of bond options. So let's compute the delta of that put option we just worked with, the European put. So the European put has a value of 0.0295 in the up scenario, and in the down scenario it has a price of 0.0054. Now, the zero rate in the up scenario is 9.67. This one you get from discount factors, and in the down scenario is equal to 4.33. So then the delta Vasicek for the put, this put, is going to be equal to minus 0.0295 minus 0.0054 over 9.67 minus 4.33. And this is going to be equal to 0.004588. Now we can also compute the delta Vasicek for the bond. This would be the 3-year bond. So this is equal to minus 0.8238 minus 0.9058 over 9.67 minus 4.33. This is equal to 0.015356. And finally, we compute the delta Vasicek of the call option, that European call. So it's going to be equal to minus 0 minus, in the down scenario we got 0.011 over same denominator in all cases, and we find 0.00206. We're now going to compute the gamma Vasicek for the securities. So first we're going to compute the delta in the up and down scenarios. So first let's do the one for the 3-year bond. Then in this case the delta plus for the bond is going to be equal to minus 0.8839 minus 0.8324 over 12.34 minus 7, and then we get 0.009079. Now the delta of the bond in the minus scenario, in the down scenario, is going to be minus 0.9324 minus 0.9835 over 7 minus 1.66, and this gives us 0.009577. Then the gamma of the bond, the gamma Vasicek of the bond, is going to be equal to minus, so this would be delta B plus minus delta E minus over R plus minus R minus. So we just replace by the numbers we just got, which are going to be minus 0.009079 minus 0.009577 over 9.67 minus 4.33, and this is equal to 0.12340 9326. Now we do exactly the same thing now for the put option. That's the European put with strike of 0.94. So we're going to find that delta plus for the put is going to be equal to minus 0.056 minus 0.0076 over 12.34 minus 7, and this is equal to minus 0.00906. And then the delta in the down scenario is equal to minus 0.0076 minus 0 over the rates, 7 minus 1.66, and this is going to be equal to minus 0.00142. So finally, the gamma of the put, it's going to be equal to minus the delta plus of the put is minus 0.00906 minus, and then minus again 0.00142. This is the delta in the down scenario, over 9.67 minus 4.33, and this is equal to 0.001431. What can we conclude here when we compare the gamma of the put with the gamma of the bond? That the gamma of the put is much larger than the gamma of the bond. Remember that the underlying security of the put is this bond. So when you buy the put, you're subject to a much higher convexity, a much higher gamma exposure. Thanks for watching.